The universe has just revealed its most terrifying secret to humanity, and what scientists discovered will change everything we thought we knew about our safety in space. A cosmic weapon of unimaginable power is pointing directly at our solar system, and the countdown to potential devastation has already begun. Subscribe now because what you're about to learn could be the most important scientific revelation of our lifetime. The energy signatures detected by our most advanced space telescopes show something that, honestly, just defies all previous understanding of cosmic phenomena. This isn't science fiction. This is the harsh reality that astronomers are grappling with right now, and the implications are beyond comprehension. Leave a comment if you think humanity is prepared for what's coming, because after watching this video, you might change your mind completely. The data is real, the threat is imminent, and the silence from major space agencies speaks volumes about the gravity of this discovery. What you're about to witness will fundamentally alter your perception of Earth's place in a universe far more dangerous than we ever imagined. The cosmic weapon that has scientists around the world losing sleep isn't some distant theoretical threat. It's an active, powerful force that has already begun affecting our solar system in ways we're only now beginning to understand. In October 2022, telescopes around the globe detected what researchers are calling the brightest gamma-ray burst ever recorded, designated as GRB 221009A. This wasn't just another cosmic event to add to the astronomy textbooks. It was a demonstration of the universe's capacity for destruction on a scale that makes our most powerful nuclear weapons look like firecrackers. The burst was so intense that it temporarily blinded satellite sensors and caused measurable disturbances in Earth's upper atmosphere, despite originating from a galaxy nearly 2 billion light-years away. What makes this discovery particularly alarming is that scientists now realize we're dealing with something that could have been far worse if it had occurred closer to our solar system. The mechanics behind these cosmic weapons reveal the terrifying truth about how the universe operates when stars reach the end of their lives. When massive stars, those at least 8 times more massive than our Sun, finally exhaust their nuclear fuel, they don't simply fade away quietly into the cosmic night. Instead, they undergo catastrophic core collapse that creates conditions so extreme that honestly, the laws of physics as we understand them begin to break down. In mere milliseconds, the stellar core compresses to densities that exceed those found in atomic nuclei, creating pressures and temperatures that dwarf anything found elsewhere in the universe. This collapse triggers a rebound effect that launches material outward at speeds approaching that of light itself, while simultaneously forming highly focused jets of energy that can maintain their coherence across billions of light-years of space. These jets don't spread out uniformly in all directions like the light from a typical explosion. Instead, they remain tightly focused beams of the most energetic electromagnetic radiation in the universe, gamma rays that carry more energy in a single photon than visible light carries in billions. When one of these jets happens to point directly toward Earth, we become the target of what scientists now recognize as nature's ultimate weapon. The gamma rays travel through space unimpeded by interstellar dust or magnetic fields, maintaining their deadly intensity across vast cosmic distances. Recent calculations suggest that a gamma-ray burst occurring within our own galaxy, and pointed in our direction, could deliver enough radiation to Earth to strip away our protective ozone layer in a matter of seconds. The implications of such an event extend far beyond the immediate radiation exposure. Without the ozone layer, Earth's surface would be bombarded by the sun's ultraviolet radiation at levels that would prove lethal to most forms of life. The marine ecosystems that form the base of our planet's food web would collapse first, as phytoplankton, the microscopic organisms responsible for producing much of our oxygen, would be among the first casualties. Agricultural crops would fail as plants struggle to survive under the intense UV radiation, while the disruption to atmospheric chemistry would trigger climate changes that could persist for decades. Scientists studying the fossil record have identified several mass extinction events that correlate with evidence of intense radiation exposure, suggesting that gamma-ray bursts may have already shaped the course of evolution on Earth multiple times throughout our planet's history. The discovery that has researchers particularly concerned involves not just the historical record of these cosmic weapons, but the current threat assessment based on our rapidly improving ability to detect and study them. Advanced space telescopes and ground-based observatories now provide us with an unprecedented view of stellar evolution throughout our galaxy and beyond. What we're seeing is deeply unsettling. The Milky Way contains numerous massive stars that are approaching the end of their lives, including several that could potentially produce gamma-ray bursts pointed in our general direction. Wolf-Rayet stars, characterized by their extreme mass loss and violent stellar winds, represent particularly dangerous candidates for future gamma-ray burst production. These stellar monsters burn through their nuclear fuel at such a prodigious rate that their lives are measured in millions rather than billions of years. Among the most concerning discoveries is the identification of binary star systems where one massive star is already in its death throes while its companion continues to evolve toward its own catastrophic end. These systems can produce scenarios where the collapse of one star triggers instabilities in its companion, potentially creating coordinated bursts of energy that could prove even more devastating than single-star events. The recent detection of gravitational waves from merging neutron stars has revealed that these cosmic collisions also produce gamma-ray bursts, adding another layer of complexity to the threat assessment. Unlike the predictable evolution of single massive stars, the timing of binary mergers involves chaotic dynamics that make them virtually impossible to predict with any precision. The energy scales involved in these cosmic weapons challenge our ability to comprehend their true destructive potential. A typical gamma-ray burst releases more energy in 10 seconds than our sun will produce over its entire 10 billion-year lifetime. To put this in perspective, if we could somehow harness just 1 second of energy from a moderate gamma-ray burst, it would power human civilization at current consumption levels for trillions of years. This energy emerges not as heat or light but as the most penetrating form of electromagnetic radiation in the universe. Gamma rays possess the ability to break apart atomic nuclei, destroy DNA molecules, and trigger cascading chemical reactions that can completely restructure planetary atmospheres. The directional nature of gamma-ray bursts means that their effects are concentrated into narrow cones of destruction that sweep across space like cosmic lighthouses of death. If Earth happens to lie within one of these cones, the consequences would be swift and irreversible. Computer models suggest that the initial gamma-ray flash would arrive without warning, traveling at light speed to reach us before any other indication of the distant stellar explosion. The first sign would likely be the sudden failure of satellites as their electronics are overwhelmed by the intense radiation. Within hours, the upper atmosphere would begin showing signs of disruption as gamma rays interact with atmospheric molecules, creating cascades of secondary particles and triggering chemical reactions that would begin the process of ozone destruction. The human experience of such an event would be unlike anything in recorded history. The gamma rays themselves would be invisible and initially unfelt, but their effects would quickly become apparent as global communication systems fail, and the night sky begins to glow with an eerie light produced by atmospheric interactions. Animals would likely sense the disruption before humans, displaying the kind of restless behavior often observed before major earthquakes or volcanic eruptions. Within days, the biological effects would begin to manifest as increased rates of cancer, genetic mutations, and reproductive failures across all forms of life. The collapse of agricultural systems would trigger global famine, while the breakdown of marine ecosystems would eliminate a primary source of protein for billions of people. Perhaps most terrifying is the realization that we would have no advance warning of such an event. Unlike asteroids or comets, which can be detected and tracked years or even decades before a potential impact, gamma-ray bursts provide no preview of their approach. The energy travels at the speed of light, meaning that the first gamma rays to reach Earth would arrive simultaneously with the first light from the stellar explosion that created them. By the time our telescopes detected the burst, honestly, the damage would already be done. This fundamental limitation of physics means that even our most advanced early warning systems cannot provide protection against this particular cosmic threat. Current research efforts focus on improving our understanding of which stars pose the greatest risk and developing more sophisticated models of how gamma-ray bursts affect planetary atmospheres. The James Webb Space Telescope and other next-generation instruments are, revolutionizing our ability to study stellar evolution and identify potential gamma-ray burst progenitors. However, this knowledge comes with the sobering realization that observation and understanding do not translate to protection. Unlike other cosmic threats such as asteroid impacts, there is just no conceivable technology that could deflect or mitigate a gamma-ray burst once it has been launched in our direction. The statistical analysis of gamma-ray burst frequency and distribution suggests that Earth faces a significant probability of experiencing a nearby burst within the next million years. While this might seem like a comfortable margin of safety, geological evidence suggests that our planet has already survived several such events throughout its history. The Ordovician extinction event, which eliminated roughly 85% of marine species approximately 440 million years ago, shows patterns consistent with the effects of a nearby gamma-ray burst. Similarly, other mass extinction events in the fossil record, they correlate with evidence of sudden increases in atmospheric radiation and ozone depletion. The discovery of these cosmic weapons has prompted intense debate within the scientific community about how much information should be shared with the general public. Some researchers argue that the statistical rarity of nearby gamma-ray bursts makes them a low-priority concern compared to more immediate threats, such as climate change or asteroid impacts. Others contend that the potentially civilization-ending nature of these events demands urgent attention and resources, even if the probability of occurrence remains low. This debate reflects a broader challenge in science communication: how to convey the reality of cosmic threats without causing unnecessary panic or diverting attention from more manageable problems. The international space community has begun incorporating gamma-ray burst monitoring into existing astronomical surveys, recognizing that early detection of distant bursts can provide valuable information about stellar evolution and cosmic phenomena. The network of gamma-ray detectors aboard various spacecraft now provides nearly continuous monitoring of the sky, capable of detecting and localizing bursts within seconds of their occurrence. This rapid response capability has led to breakthrough discoveries about the physics of these extreme events, but it also serves as a constant reminder of the universe's capacity for sudden and overwhelming violence. Advanced computer simulations of gamma-ray burst effects on Earth have revealed scenarios that range from manageable disruption to complete biosphere collapse, depending on the distance and orientation of the burst source. These models suggest that humanity's best hope for surviving such an event lies not in prevention or protection, but in preparation for the aftermath. Underground facilities, preserved genetic material, and robust food storage systems could potentially allow small populations to survive the initial radiation and subsequent ecological collapse. However, the scale of such preparations would require unprecedented international cooperation and resources that currently seem beyond our political and economic capabilities. The philosophical implications of living under the constant threat of cosmic annihilation have really started to influence discussions about human space exploration and colonization. If Earth remains vulnerable to destruction by forces entirely beyond our control, the argument for establishing self-sufficient human settlements on other worlds becomes a lot more compelling. Mars colonies, lunar bases, and space habitats represent not just scientific achievements or economic opportunities, but potential insurance policies against the ultimate cosmic threat. The development of such settlements would need to occur on a timeline that acknowledges both the statistical likelihood of gamma-ray burst exposure and the technological challenges of creating truly independent human communities beyond Earth. Recent advances in our understanding of stellar evolution have also revealed that the universe's capacity for producing gamma-ray bursts is not constant over time. You see, the early universe contained a higher proportion of massive stars, suggesting that gamma-ray bursts were more common in the distant past when life was first emerging on Earth. This historical perspective raises some intriguing questions about whether the relative rarity of nearby bursts in recent cosmic history has been a necessary condition for the evolution of complex life. If so, our current existence might represent a brief window of cosmic calm that could end at any moment. The detection of gravitational waves from merging neutron stars has added another dimension to gamma-ray burst research, revealing that these cosmic collisions can produce bursts of gamma radiation that follow different patterns than those from collapsing massive stars. The ability to detect both the gravitational waves and the electromagnetic signature of these events provides unprecedented insights into the physics of matter under extreme conditions. However, it also confirms that there are multiple pathways to gamma-ray burst production, making the threat assessment more complex and potentially more urgent than previously understood. As our technological civilization becomes, increasingly dependent on satellite communications, GPS navigation, and electronic infrastructure, our vulnerability to cosmic radiation events continues to grow. A gamma-ray burst that might have caused primarily biological damage to earlier human societies could now trigger cascading technological failures that would cripple modern civilization even before the ecological effects became apparent. The interconnected nature of global systems means that the failure of satellite networks could disrupt everything from financial markets to food distribution, creating social and economic chaos that could prove as devastating as the direct radiation effects. The search for potentially habitable exoplanets has also been influenced by gamma-ray burst research, as astronomers now recognize that planetary systems located too close to massive star-forming regions face regular exposure to sterilizing radiation. This cosmic perspective on habitability suggests that life-bearing worlds might be much rarer than previously estimated, concentrated in galactic regions that offer relative safety from the universe's most extreme phenomena. Earth's location in a relatively quiet spiral arm of the Milky Way might not be coincidental but rather a necessary condition for the emergence and persistence of complex life. The study of ancient ice cores and geological formations has revealed evidence of several sudden increases in atmospheric radiation over the past 100,000 years, some of which correlate with the expected arrival times of gamma rays from observed supernovae in nearby star-forming regions. These historical records suggest that humanity has already survived exposure to several minor gamma-ray events without recognizing their cosmic origin. The fact that our species persisted through these events provides some cause for optimism, but it also highlights our ongoing vulnerability to more powerful bursts that could occur with little warning. Military and defense organizations around the world, they've started to incorporate gamma-ray burst scenarios into their threat assessment protocols. They're recognizing that, such events could actually trigger international conflicts as nations scramble to secure resources in the aftermath of ecological collapse. The potential for widespread agricultural failure and population displacement, it's daunting. It could destabilize entire regions, creating refugee crises and resource competition on a scale that would honestly challenge existing international institutions. Now, emergency response planning also includes considerations of how to maintain social order and governance in scenarios where, let's face it, technological infrastructure has been compromised and food production systems have failed. It's a lot to think about. The economic implications of gamma-ray burst preparedness present, some pretty complex challenges for policymakers who have to balance long-term species survival against those immediate social and economic needs. Investment in underground facilities, radiation shielding, and emergency food storage, all of that competes with funding for education, healthcare, and other really pressing concerns. The statistical nature of the threat makes it difficult to justify massive expenditures for an event that might not occur for thousands of years. Yet the potentially catastrophic consequences of unpreparedness argue for taking the threat seriously, no matter how unlikely it may seem. Educational institutions have actually begun incorporating cosmic threat awareness into their curricula, recognizing that future generations will inherit both the knowledge and the responsibility for dealing with these ultimate challenges. Students learning about gamma-ray bursts today will become the scientists, engineers, and leaders who must develop and implement humanity's long-term survival strategies. This educational emphasis really reflects a growing recognition that cosmic threats represent a fundamentally different category of risk, one that requires new approaches to planning and preparation.